Hey y'all! So today we're going to be starting our review for our CBA. This is going to be the easiest CBA you'll probably have all year. It usually is, so don't stress out about it. Kids usually do very, very well on the CBA. And it's just on these few teaks that we've already learned and you're already proficient at. So the teaks that are going to be on there is 5.5A, properties of matter. Okay? 5.5B, mixtures, solutions, heating and cooling, forms of energy, and electricity. So, without further ado, we'll go ahead and we'll dive into each one and we'll talk about what we've learned and go over some of those tricks that we use to remember stuff. Okay? Okay, so let's talk about our properties of matter, right? There's 8 properties that we talk about in 5th grade science, because in 5th grade you're no longer doing the whole baby thing whenever you look at something. You're no longer going, ooh, it feels smooth, it's pretty, it's colorful, it's, you're not describing just what you see, but you're describing other properties of matter that you're actually going to test out. So, one way that we remember all the 8 properties of matter that we test in 5th grade is we came up with my mom, Vay, plays Roblox till Saturday evening. And each capital letter stands for a property of matter. So let's start with the first M. Who thinks they remember? Mass, right? So mass. Mass is just something, just how much matter is in an object. If you pick up an object like this marker and you want to determine the mass of it, I'm going to put it on what? Triple beam balance. And in that triple beam balance, I'm going to slide my little sliders over until it balances, and boom, that's how many grams this marker is. Okay, that's how much mass it has. Remember, mass is not weight. Okay, mass is how much space an object takes up. It's how much matter is in something. Hold on. Mass is how much matter is in something. Volume is how much space it takes up. Anyway, jumping ahead. This marker. If it's here on Earth or if it's in outer space, it's going to have the exact same mass. Meaning, it's going to need this much room to squeeze in through something, right? If it goes up to the moon, though, where there's less gravity, then it's going to weigh less. But we're not talking about weight. Okay, we're just talking about mass. How much matter is in this thing. All right, next, let's talk about the next M. Magnetism. Okay, and when you talk about magnetism, it's whether or not something is magnetic. Remember, you must always have a positive and a negative together. Okay? 2 positives repel, 2 negatives repel. You always want a positive and a negative because they're just like besties like that. Here, we'll put here, triple beam balance. And we'll say it's measured in grams. Alright, so magnetism, if it's just magnetic or not. Too easy, right? Alright, the V is for volume. Volume. What? Okay. And is it that kind of volume where your voice gets much louder? No. It is straight up just volume, like how much space something takes up. So if I have a graduated cylinder, ooh, we're going to use a graduated cylinder for this. Come on now. Graduated cylinder. And we're going to fill it with some water. Maybe we'll put like 50, grams of water? Or 50 milligrams? Or 50 milliliters of water? Okay, fill it up, put a little 50 milliliters in there. Drop the marker in. Is that water going to rise a little bit? I see one of you say no. Stop. Yes, it's going to rise a little bit, all right? And as it rises, then you subtract the 2, right? You subtract the new level versus the original starting level. And then that's your answer. That's how you get your the volume of this marker. All right, this one's easy, guys. Physical state. Physical state. Who remembers that we came up with that? So remember that. I'm going to go over here and do SLG. Do you remember? Silly little geeks. But what is it really? Physical state, silly little geeks, solid, liquid, or gas. Okay? solid, liquid, gas. Okay. Again, you're looking at marker, and you're going, my big science brain, I think it's a solid. And you hear, like, in the background, you hear, like, the cheering noise, like, because you're so smart. You knew it was a solid. All right, moving on to the R. This is one of my faves. What does the R stand for? The Roblox. What is it for? Relative density. And we all know what that means, right? That means if I go and put this in a cup of water, and if it sinks, it's going to hit the floor, and we say that's mo flow, because if it hits the flow, it must be mo, right? Mo flow. Mo flow. If it's mo, it's on the flow, right? If it's more dense, it's going to sink, and when it sinks, it hits the bottom, which is closest to the floor. Which is more dense, oil or water? Water, because the oil floats on top, right? That's less. Cup of water. We'll do a paper clip and a ping pong ball. That ping pong ball is less dense, right? Less dense than the paper clip. The paper clip is more dense because it's on the flow. So the ping pong ball is less dense than the water. The water is less dense than the paper clip. Okay. All right. T. T, 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 T. What time is it? T, T, T. It's thermal energy time. Thermal or conductivity, we could say. So if it's conductivity, okay. Thermal conductivity, right? Does it get hot or not? Say, if I, cooking pot, right? The pot itself is going to get hot. We know if I'm cooking with it. But that handle that they put on the side, it's made out of rubber or plastic so that I can actually grab it and not burn my hand off. Okay. Thank you, designers of cookware. That doesn't get hot. It does not have thermal conductivity. It does not heat up. Are your feet conductors of thermal energy? Well, you ever walked outside, like you're on the pool in the middle of like July at not spare time, what is that place called? Lions Junction, right? And you're walking around and you're like trying to get to that big slide and you're like, hot, right? Because the ground is super hot and it's transferring that heat to your feet. So, thermal conductivity, if thermal energy can flow from one object to another. All right, S, what's S? Solubility, which just means what? Does it dissolve? It dissolves. Okay. If I stick this marker in that cup of water and then I'm going to stir it up, because I saw once on TV that you can actually dissolve this. Is it going to work? I think I saw that on the fake media. I think it was the fake media that showed me a marker dissolving when I put it in water. But, no. So, solubility, does it dissolve? We do know that salt, right, plus H2O equals dissolves. What about, so salt and water dissolves, right? The salt dissolves in the water. What about sand and H2O? Does that dissolve? No dissolvo. If it did dissolve, would we have any beaches? No, we wouldn't. That'd be so sad, okay? Because I love to go to the beach. All right. And last but not least, the E. What is the E for? Electrical. conductivity. Same thing as like the thermal, right? Either electricity can go through it or it can't. Can electricity go through rubber? No. Can electricity go through metal? Yes. Can electricity go through this clothing, this cotton? No. Can electricity go through my jeans? No. Can electricity go through this plastic chair to my right that you do not see? No, because it's plastic, right? Can electricity go through this metal that you hear? Yes, right? Remember, electricity, metal equals heavy metal, rock and roll, right? Alright, so these are your properties of matter. These are the things you need to know for the test. Think, if you see a properties of matter question, which you're going to see, because there's going to be a bunch, just think thoroughly. Remember your cheats. Write your cheats out, okay? And, yeah, you'll be fine. So, alright. Alright, so now we're going to talk about mixtures. We're going to mix it up with some mixtures. Remember the thing about the mixtures is that you can easily separate it. So when you're done mixing with your friends, you can easily separate, right? So let's talk about some mixtures. How about Chex Mix? Right? I actually had a party this weekend, y'all. It was lit, okay? And it was for my son. It was his birthday. But we had some Chex Mix. And I saw one of my old lady friends, she didn't like the peanuts, so she was picking them out of that Chex Mix and just putting them to the side. But she could do that because it's a mixture, right? And we know that what a mixture is. This is the key part you need to know. Easily separated. What? That's important to know. Alright, what other items are mixtures? Can we do, how about a salad? Okay. Oh my gosh, my shoes. Y'all, in my closet, I have about 120 pairs of shoes, maybe 130, okay? But my shoes, right? If I wanted to say, winter's coming, so I'm going to put all like my sandals away, and I'm just going to get out my boots, because it's boot weather, and I love boots, okay? Those are mixtures. I can easily separate them. Now let's get a little deeper now, like what we did in the lab. What about sand and water? Is that a mixture? How? Somebody tell me how. Can you easily separate sand and water? Yes. What are some tools? What are some science tools you would need? You would need a filter, or what is it called? It's called a sieve, a filter, strainer, okay, all those things. I'm going to put sieve, because remember I told you that's the one word that you might see on STAR tests, and you might not actually, you just need to know it, okay? Anyway, sand and water, so you can just pour the whole mixture through the sieve, and it'll, what am I saying here? Why would I want to use a sieve for sand and water? Y'all have got me all miscongratulated. Y'all are not squaring me away. I don't want to use sieve. What do I want to use? Come on, get your lives together, people. A coffee filter. Why would I want to use a coffee filter for my sand and water? Because the sieve, the sand might actually go through, and then we really have not separated anything. But the coffee filter, it will actually hold the sand, and the water can filter through. Okay. But let's go back to that sieve, because it's really got that sieve on the brain. What can I use the sieve for to separate? We did it in the science lab. Okay. Can we still use the sand in the sieve for something? I'll put here sieve. because I really want to use that seed. We can do sand. And what do you think? How about the rocks? Gravel, okay. Sand and rocks. Do you remember, guys, when we had in that big mixture? Okay, help me think. What do we have? What do we have in there? I know we had the sand. Okay. I know we had the rocks. I know we had the iron fillings. Filings, or maybe it's filings, whatever, stupid. And we had the wood chips. Okay. Who remembers how we separated it all? What did we start with first? I think we started with the iron filings, whatever. And to get these jokers out, what did we all remember using? Magnet, right? We just ran the magnet over the entire mixture, and it picks up all the iron filings. Okay? Do you remember that? I do. And then we just had these three things left, so we'll cross this one out. We had the wood chips, the sand, and the rocks. So what do you think we could do next? We could do the sand. I think we did the sand next, right? Because for that, we used our sieve. So we'll come down here, and we'll say we use the sieve. Oh, squeaky. Ugh. All right, so use the sieve, and that left us with just two things, the rocks and the wood chips. Now, what do you remember we did to get the wood chips and the rocks separated? We added something. Water! Water! Why would we want to add the water, yo? Let's see how I want to do this. Why did we add the water? We added the water so that the rocks stayed on the bottom, right? Remember? Because they were like more dense, they were more flow. And the less flow were the wood chips. They floated, okay? And then as they floated, then we could take like a scoop, or I think y'all use spoons. Some of you try to use tweezers, but you could use something like basically a spoon, right, to kind of like scoop it all out. So after the water, you can use a spoon, and you can spoon them out, and then all you have left is your rocks. Now, if you still want to get the water out, you could go to the rocks. You could either use another sieve. You can use a sieve. You could try to use a sieve, provided that the holes are small enough, or you could just do another paper filter, coffee filter, whatever. Okay. And that is how you separate a mixture in the science lab. And now we're going to move on to our solutions. So, sometimes you're like, come to me with your little problems, and I'm like, dude, find a solution for your problems. Just messing with you. Solutions. Okay, those are things that you still combine two or more ingredients, but they cannot be easily separated. So, we'll just put here, not easily separated. Okay, let's talk about some ideas of things that are not easily separated. Let's go easy. First one, right at the top of your head. Salt and water, right? I know, y'all like it when I do right, like a real scientist. All right, salt water. Can you still separate salt water though? Yes, you can. Is it easily? I mean, can you just walk into a room and just boom, separate it? No. What do you have to do to separate the salt water? You have to boil it, right? Boil it, because when you boil it, all of the water evaporates, all right? And what's left? Remember when I had the beaker and I put way more salt in there than I thought I did? And at the end of the experiment, all that was left was that big, thick white film. That's all salt, right? Love my salt. What about sugar and water? Can sugar and water be easily separated? Same thing, right? What about, can, is honey and water a solution? Yes, because honey dissolves. Remember, I told you were probably going to see a question about that on test. Honey does actually dissolve in water, okay? If not, why would people put honey in their tea? Speaking of tea, which dissolves sugar? Hot water, cold water? Hot water. If you want the sugar to dissolve, you're going to have to put a little heat to it, okay? Let's come up with something like that. It just kind of coming to me right now. Come on, man. Work with me. Want something sweet? You get ready for this? Want something sweet? Heat it up. Heat it up, baby. Turn up the heat. You want something sweet? Turn up the heat. Oh, there we go. Want something sweet? Turn up the heat. Want something sweet? I like that. Take this off. Want something sweet? Turn up. Duh. Put duh. Heat. You want something sweet? Turn up the heat. I like that. I'm rolling with that. I can't wait to see all these do that. Okay, so solutions, not easily separated. You can separate it, but it's not easy. You gotta do a little something extra. We watched that video where that lady goes into the whole NASA chemical lab, and remember they separated like all kinds of crazy stuff. Almost everything in the world can be separated. You can actually separate almost every element from the other elements. However, you just have to have a lot of special equipment. Again, mixtures and solutions is super easy, especially in 5th grade. You're all prepared, so I'm not really worried about it. Just remember, honey does dissolve in water or tea. Okay, otherwise them old ladies would not be putting it in their tea, because honey's not cheap, and you know old ladies are stingy with their money. And if you want something sweet, you gotta turn up the heat. Oh, I like that. Alright, this next one I'm gonna go through real fast because this was a 3rd grade tea. So you learned this 2 years ago, you hit on it again last year, and we hit on it again already this year. This is heating and cooling, 3.5C. Okay, this is easy, but so a lot of you get it mixed up in your head. So I'm gonna help you remember one more time. Alright. Boiling. In order for water to boil, like hot, like so hot, you don't really want to get in there and take a bath, right? What temperature does it have to reach to start boiling? Now that doesn't mean the temperature hits this number and the whole thing is just like, okay, it's not. It's just starting to boil. So what's that number? Remember, I already told you. You only got 2 numbers to know when it comes to this topic. Right? 100 degrees Celsius. Some of you are already thinking 0. Punch yourself in the head. Just kidding, don't punch yourself in the head. Alright. Freezing point. What is the freezing point of temperature? What does the water have to get to start freezing? I'll give you a hint. It's not that number. Yay! 0 degrees Celsius. Yay! Alright, we're good. We're good. We got two so far. Now, the tricky one. What does the temperature have to be to start melting? Remember, to start melting. Is it 0 degrees Celsius? Who's confused? Oh my God, how can that be 0 degrees when that is 0 degrees? Lazy ice cube. Remember, guys, the lazy ice cube. Actually, you're the lazy. But I'll give you the lazy ice cube story. This is more so for my friends that weren't here at the beginning of the year. Alright, so here's what happens. You go in the kitchen, right, and you get a cup of ice. You, put it underneath the thing, or you get it out of the freezer with your hand, whatever, right? And it drops on the floor. And that one piece does. And you look around. Mom's not in here. Husband ain't in here. Kick it underneath the fridge, right? Nobody ever has to know. When that ice cube was in the freezer, would you say it's at 0 degrees Celsius? Or probably colder, right? I mean, if ice starts freezing when the temperature hits 0 degrees, then in order for it to completely freeze and to stay frozen, it's going to be even colder, okay? But in order for ice to start melting, that temperature has to rise back up, right, from the negative numbers. And once it hits that 0 degrees Celsius, and it's no longer in a cold place, it's now in a warmer place, then it starts melting. So that's how those two numbers are actually the same, is because they're the starting points. Water starts to freeze when it hits 0 degrees Celsius. When that ice warms up enough that it finally hits 0 degrees Celsius, then it starts to melt. Okay? And then once it just keeps rising and rising, and if you add a little heat to it, then you got some boiling water. And eventually that boiling water turns into what? Gas, which is our shower scene, right? You turn on the shower, you let it run and get all hot. And as it's hot, it's getting hot, you go and you open the shower door and you're like, whoo! All that steam comes out, right? And you're like, yeah, it's going to be a good shower. So you get in and you're washing your arms and your hair with your little rubber ducky, and you get out, and all of a sudden the mirror is completely fogged. You can't see yourself. And the bathroom's just all humid, and you're like, oh, I can't breathe. Because all of that vapor that was in your shower, it comes out. And it hit that cold mirror. And when it hits that cold mirror, it turns back into condensation. Oh no, I gotta go. It turns into condensation. And as it condenses, then it starts to turn back into water, and it drips all the way down your mirror. And that's heating and cooling. Okay, so our next teak is 5.6a, forms of energy. And this is the teak that I'm just melting for. I'm just melting all over it, because I just love this teak. Okay? What am I doing? Remember this? I am using, right, mechanical energy, but what am I producing? Thermal energy. Remember that vocab I wanted you to learn. No, you have to pay attention to this. Produce and use. Pay attention to that in those questions, guys, and circle those words. Produce or use. M, what does it stand for? Mechanical. E, what's the E, y'all? Electrical. And L, what's the L? What color is that? Pink. Oh, snap. Light. Then we have the T is thermal. And last, what's the last one? What? What's the last one? What? Sound energy. All right, so let's talk about these uses and produces, okay? Mechanical, my mechanical is producing thermal energy. I'm going to take that thermal energy and I'm going to transfer it to my face, because my face is cold. Okay, and for a split second, it kind of adds a little warmth to it. In this room, this light board room, this is a great example of melts. The lights are producing light energy, and I am using it so that you can see me. Well, that was really not a very good example. Okay, back up, rewind. Okay, the lights are using electrical energy, right? Because the plug is in the wall, and the energy is pulling the energy out of the wall, and it's going up and making the light come on so you can see me. Check out my hair. So it's using electrical and producing light. I am using the light to produce a review for you with all my mechanical energy. Alright? And I am also using mechanical energy to produce sound to you, because I'm giving you some sound. Yeah, I think we're good on that. I'm not going to go anywhere else. These are the two words I really, in all seriousness, circle these on those questions. Circle it so you know what they're asking. If they're saying, what does it produce or what does it use? Because if you don't, you're going to get it wrong, and I will come by with that 2x4 and maybe use some mechanical energy. Alright, now we're on to everyone's favorite teak. At least I think it is. Some of you say this. We're on to circuits. Oh man, circuits are so fun. Circuits are fun once we started having fun with them, right? You start understanding the difference between the open, the closed, the series, the parallel. Okay, so let's hit it. Alright, 5.6b, circuits. Let's start here. Open circuit. You like up here? Break my heart. Oh, why is my heart broke? Because my light don't come on. I mean, you got literally a break in my circuit. There's a break. It's missing a wire, okay? I was gonna trick you and put the wire like this, because I know a lot of you would still say that's a closed circuit. Just, honey, just because there's two wires and they're connected on the light bulb does not mean it's a closed circuit, because it's got to be on the other side, right? Alright, so this is broken heart. Buh, you broke my heart. Now, come over here to the cool side, the closed circuit. Look, you complete me. Aww. Okay, I don't know why I'm being all weird today. I think it's a lack of sleep. Alright, so you got your circuit. You got your light bulb, you got your battery, you got the positive side, negative side, you got wires. You got this little path here. These little electrons are just going wee, 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 right? All day long, okay? And they're just happy-go-lucky because they're just like going in circles. I got nobody stopping them. Now, notice I don't have a switch here. Do you need a switch to build a circuit? No, do not. What the heck? Need switches. But do we want switches sometimes? Yes, because if we didn't, these electrons are going to get so worn out that the battery's going to die, okay? So you want a switch, so you can turn it on and off, right? That's not going to work. That works. But to me, it's boring. That's what brings me to my simple. Two types of circuits, guys, series and parallel. It's the series that are the boring ones. They're simple. They've got no life choices, okay? They're literally, remember when I used the batteries like the house, and I was like, you're coming out of your house, you can go out the front door or the back door, it doesn't matter, but you're going to go and you're going to find whatever it is you're supposed to power, and you're going to flow through it, and you're going to come back to the, if you went out the front door, you're going to come back to the back door, okay? You got to make that path. You got to be a complete path in order for your device to work. I can't tell you how many of you knuckleheads were putting those batteries in the other day. It was just cracking me up, actually. All right, but it's boring, right? It's a boring circuit. It's simple. It's boring. It's, okay? Even the electrons are so bored, okay? They want life choices. And when I say life choices, what kind of circuits am I talking about? I'm talking about them parallel ones, man. Them parallel ones, those ones get complicated. Those are the fun ones. So, let me get rid of all this. Alright. Parallel. This is a parallel circuit. You know why? Because this joker's got choices in life, okay? He's got choices. He gets to get those Y intersections in life. The one where it's like, oh, should I go here? Should I go there? What? Alright. Right now, I can look at this and tell that it is a closed circuit, okay? This one completes me. This one, my heart is complete. And how you know that is you're going to start at the battery. We're going to say this is the front door, okay? The positive side. So I'm the electron, right? And I really don't want to sing this song right now because it's going on YouTube and I don't know who else is going to see it. And you know that song has never got the lyrics finished. Okay, so we're going to start from the front door and we're going to... Alright, so far so good, right? He's in the switch. The switch is closed. I'm just going to tell you that right now. So the electrons can go through. They're going to come out the other side. Okay? Now, when I say choices in life, he gets here. He's got a choice in life. He can continue to go this way, or he can come down this way. Okay? So, pick a path. We'll go this way first. Okay? And again, he got another choice in life. He's got a little Y intersection. You see that? He can go that way, or he can come back down this way. And we're just going to keep going this way. And he doesn't stop till he gets to the back door of his house. Alright, he just made a complete path, right? Yes, he did. So, now if we wanted to figure out our life and see, let's say, let's be mysterious and let's check this other path. So when he got here, when Mr. Electron got here, and he decided to go this way, okay, if he stops right here, does he have a complete path? No, because what does he need to get to that? Okay. So he'll come here, and then these electrons go here. There he goes. And now, oh wait, hold on. Where didn't I? It comes through here. Sorry, I got a little carried away. Alright, so now you got two paths. What if take this. Some little kid came along and decided to mess with my circuit. So what's going to happen when the electron gets to his Y intersection and he decides to go this way? What happens when he gets to the edge? Remember we were talking about like getting to the edge of a cliff and you're like, whoa, can't really go anywhere, right? So this is not going to work. When he gets here, can he still go this way to make his path? Yes. So remember, if you have a choice in life, you're parallel. If you don't, you're simple and boring. What else I want you to know? Insulated wires, guys. Come on, wires. Here. Wires are metal. They're copper, right? I can't see that again. Wires equal metal. And in order for electricity to flow, you have to have metal to metal, which is heavy metal. Which is why we listened to a bunch of awesome 80s rock songs while we were doing circuits in the science lab. Heavy metal, rock and roll, baby, what's up? see. Conductors, things that are conductors, pennies, because it's still copper. Why do they put the rubber on the wire? Like this right here. There's a lot of electricity going through here, okay? All the lights and stuff. And thankfully some genius decided to cover these copper wires with rubber so that I can hold this and not have bad hair day. Thank you, rubber genius. Alright. I think that's it. Any questions?